From this lecture we will start number systems. Number system defines a set of values used to represent quantity. Let us consider any quantity, and this quantity is represented by decimal number 7392. This is in decimal. We can also represent the same quantity in any other number system like binary, octal, duodecimal, hexadecimal. The decimal number system is the most popular and common number system which we use in our daily life. If we have to measure the distance, weigh something, or count our money, we use decimal number system. There are 10 different digits in decimal number system from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the 10 different digits in decimal number system. In case of binary number system, we have 2 different digits, and 2 is the base for binary number system. Now what is this base? The base of a number system is also called as radix. The base is also called as radix, and because of this r, the notation for base is a small r. Now the base will tell us how many distinct digits we have in a number system. For example, in case of decimal number system, the base will be 10 because we have 10 different digits in decimal number system. For binary we have 2 different digits. Now what are these 2 different digits we have to find? The digits will start from 0 and there will be increment of 1 every time, and it will end to r minus 1, where r is the base, and in this case r is 2. So 2 minus 1, this will give us 0 and 1. So there are only 2 digits in case of binary number system, and in binary number system we do not call them digits but we call them bits. And as there are 2 numbers, we call this system binary number system. In case of octal, the base is 8, so we definitely have 8 distinct digits in case of octal number system, and they are from 0 to 8 minus 1, and this will give us 0, 1, 2, 3, 4, 5, 6 and 7. So these are the digits in case of octal number system. For decimal we have already seen 0 to 9, 10 distinct digits. For duodecimal, the base is 12, so we have 0 to 12 minus 1, and this will give us 0, 1, 2, 3, 4 all the way to 9. And then we have A. We represent 10 as A, 11 as B, 12 as C, 13 as D, 14 as E, and 15 as F. This is how we represent 10, 11, 12, 13, 14 and 15. So 10 is A, 11 is B, and we only have 12 distinct digits from 0 to 11, so we will have 0 to B in case of duodecimal number system. For hexadecimal, we will repeat the same process. 0 to 16 minus 1. 16 minus 1 is 15, so we have 0 to 15. So 0, 1 all the way to F, because F is 15. This was the small introduction on number systems. In the coming presentations we will see more details on them. We can also have a number system with base 4. We can have base 4, and in this case we have 0 to 4 minus 1. So we have 4 distinct digits, and they are 0, 1, 2, 3. Very simple. So if we know the base, if we know the radix, a small r, we can definitely find the different numbers in the number system. Now we will move to next part of this presentation, in which we will discuss weighted and unweighted codes. The number 7392 can be written as 7 thousands, 3 hundreds, 9 tens and 2 ones. This is how we can write this number. Or I can write 7 multiplied by 10 raised to power 3, 3 multiplied by 10 raised to power 2, 9 multiplied by 10 raised to power 1, and 2 multiplied by 10 raised to power 0. This is how we can write the number 7392. The weight of this position is 10 raised to power 0. The weight of this position is 10 raised to power 1. Weight of this position is 10 raised to power 2, and weight of this position is 10 raised to power 3. Generally the coefficients 7, 3, 9, 2. These are the coefficients, and generally the coefficients are written and the power of 10 is determined by their position. The number system with weights on position we call weighted number system, and the number system in which there is no weight on the position we call unweighted number system. So the number system and codes we can categorize into two groups. The first one is weighted and second one is unweighted. In weighted we have few examples. First one is decimal number system that we have seen here, the decimal number system. The second one is binary, of course, octal, binary coded decimal, etc. These are the examples of weighted number system. Examples of unweighted system are gray code, XS3 code, etc. So this is how we can classify the number system and codes depending upon the weights on position. Now we will move to the next part and the last part of this presentation, in which we will compare binary, decimal, octal and hexadecimal number systems. Let's say there is a quantity. We are representing this quantity in a number system with base R1. R1 is the base of number system, and let's say capital N1 is the total number of digits, required to represent this quantity in this number system. Let's say there is another number system. We are representing this quantity in another number system, and the base for this number system is R2. Capital N2 is the total number of digits used to represent this quantity, and for an instance, let's say R1 is smaller than R2. The base R1 is smaller than the base R2, then capital N1 is greater than capital N2. This is very important point. When we increase the base, when base increases, the digits required to represent the quantity decreases. For example, 7392 is the decimal number which is used to represent the quantity. Then in binary it is represented, the quantity is represented by 11100110000 in binary. So you can clearly see the number of bits are way more as compared to the number of digits in decimal, because base of binary number system is 2 and 2 is smaller than the base of decimal number system. If I represent the same quantity 7392 in octal, then I will have 16340. This is in octal. We definitely have reduced the digits as compared to the binary number system, but we still have more digits than the decimal number system. In decimal we are having 1 2 3 4 4 digits, and in octal we have 1 2 3 4 5 digits, because in octal number system the base is 8 and still 8 is smaller than 10. Now we will represent the same quantity in hexadecimal. In hexadecimal it is equal to 1CE0. This is in hexadecimal. Now there is one important thing that you can see. Here we have 4 digits, and in this case also we have 4 digits. So we can say that N1 is not strictly greater than N2, but they can be equal.